Hi everybody, this is Konstantin Läufer, your Comp 413 instructor at Loyola. And the purpose of this video is to get us up to speed on Project 2, which is the first somewhat more serious Android app. Nevertheless, it's still an output-only app in the sense that you launch it and expect to see what's on this picture. There's no interaction with it. In the hello example, there was the capability of interaction in the app, meaning you could press long or short and you would get a different response. Here, there's no such thing, no input. It launches and just draws something, and it's supposed to match what you see here. And it's similar to Simple Batch and Simple Draw. So Simple Batch is kind of a console app that runs on Android, meaning you can produce whatever output you want and it'll just show up on your screen. And Simple Draw is the equivalent, but for a graphical drawing. And this Shapes project is based on Simple Draw and gives us an opportunity to pursue these learning objectives. In particular, what we will be able to see is these kinds of design patterns that are familiar in the object-oriented community. So if you were using a more conventional object-oriented language like C++, Java, or C#, you'd be seeing these patterns applied in a more direct sense. Now in Scala, there are slightly different, easier, more straightforward ways to achieve the same effect, and that's what we're seeing here. And let's take a quick look, and we'll go back and forth. Okay, so if we go over to the code base, the first thing to do is, well, keeping in mind that we're supposed to ultimately produce the same drawing as on the screenshot, the next thing to see is what is marked here as to do. So we can say view tool windows to do, and we'll see that there are basically 3 to do items. And the easiest one is perhaps this size visitor here, but there isn't really anything there. So let's understand what this does shortly. The other to-do items are the bounding box visitor and the draw one. So those are the 3 that come up here. But before we get there, let's look at a little bit of background in terms of our data model. And if you look at the shapes file here in the model, you see a whole bunch of different things here. Some of them are even there twice, and we'll find out what that is all about. The good thing is I made this easy by providing a full implementation of the shapes domain model. So this is your domain model or object model. So this is the part for which you would typically use the composite pattern in conjunction with things like decorators, and then to actually bring behavior into the picture, to bring in these behaviors in the form of visitors. Okay, well, let's look at a more object-oriented way of expressing these things. So your practice midterm here, what this shows you first, okay, is a basic graphics library that's not object-oriented. And in a way, in the project, this role is played by the Android canvas and paint object. So the canvas has support for drawing a circle, drawing a rectangle, drawing lines, and so on. So what we're doing is essentially mapping the way a possibly complex graphical shape is drawn onto the Android canvas. So in that sense, the canvas corresponds to this basic graphics library. And this is the part here that corresponds to our shape and its implementations. Except our shape is just a name. It doesn't have any capabilities. These capabilities here are to illustrate that you can have behaviors directly present in the object model, like the draw here. That's a method you invoke directly. Or you can have the visitor pattern. So the accept method equips the object model for working with the visitor pattern. And then you can pass in any kind of behavior as a visitor. And then that behavior has basically a case distinction that corresponds to the existing concrete implementation classes of the common abstraction, in this case shape. Okay. So normally you do either the behavior in the object model, like the draw, or you do the visitor. But here it's just for studying this that we have both. And there is, of course, an important trade-off between using the visitor to add behaviors or not using the visitor. Okay. And maybe that trade-off we'll discuss on Facebook. That'll be an opportunity for us to get engaged in a little discussion here. Anyway, so the shape is the common abstraction, and then we have implementations such as circle and rectangle, and their accept methods are just basically saying, well, if you're in circle, you say, well, you tell the visitor, visit me as a circle, me being this, and the object on which you're invoking the accept method, current receiver. And on rectangle, you say, well, I'm a rectangle, so you tell the visitor, visit rectangle, and the rectangle, that's me, because you just invoke the accept method on me. Okay, now the first part here, and these things are done already in the project skeleton, the Android project skeleton. But here it's part of the exam, and the solutions are here. They're linked at the very bottom of the exam itself, and they download as this text file. So basically the complex shape has this list of shapes that are the children. And that's 1/2 of the composite pattern, meaning the composite is composed of 0 or more of the original kind of things, which are shapes. And you also see that this Java code precedes genericity in Java. So this is a non-generic way of expressing this, but it really doesn't matter that much. You just have to cast further down. You have to cast back to shape as you work with the items in this list. So the other part of the composite pattern, what makes this complex shape be really a composite, is the fact that it also is a shape. So complex shape has a bunch of shapes, the children, but it also is a shape. And that second part means, oh, now I can put a complex shape inside a complex shape as a child. So I get arbitrarily deep nesting or arbitrarily deep hierarchies. If I didn't have that implement shape part, I would not be able to nest it. So that's the kind of the beauty of composite. You have has 0 or more of the common abstraction, but it also is one of those objects represented by the common abstraction. And that gives you this arbitrary hierarchy capacity. So what we have now is we have basic things like circles or rectangles. Those are not composites. Those are leaf nodes. They don't have children. And then you have things like complex shape that is there specifically as a grouping construct that has 0 or more children. Okay, and you see the fixtures here. Basically, let me show you the actual shapes. So you have group, that's the equivalent of complex shape, and you have the children right here, and the asterisk means it's 0 or more. And any Scala specific syntactic questions, my recommendation is to consult the Horstman book, which is excellent. So what you would do is just look at the Scala coding topics here and consult Horstman Scala for the impatient by need as you encounter these in the code or in conjunction with looking at the project instructions. So the only thing that's required for this group object is that children be a proper, basically a sequence. So the star is for var args, but var args, variable number of arguments, 0 or more, gets represented as a sequence, meaning typically a list in Scala. Okay, and the only requirement is it cannot be null and there cannot be any null children. So if there are any children, they have to be non-null. And then there are a whole bunch of other things here. So circle, and circle happens to be a case class, and group happens to be an ordinary class. And that's really just a workaround the fact that in Scala you cannot inherit from case classes, but we want group to be usable like a case class, as we're about to see in the fixtures, but we still want to be able to inherit from it, so it cannot be a case class. But by providing this companion object, which has the apply method that acts like a constructor, and the so-called unapply method, which acts like an extractor for pattern matching. So this is quite a bit of stuff, so let's look at this piece by piece. So first of all, to construct instances of case classes, the beauty is, now I corrected this, whoops, I want to make this bigger. The beauty is, what do you see that's not there? That's right, there's no new operator anywhere here. So if you have a case class, you can simply create these instances without saying new every time. And that essentially reduces the amount of noise in there, because you just want to create the instances. Very good. And then the other part is, when you look at the way you operate on these kinds of nested object trees that are built from these case classes, you can then, when you create a behavior on that, so the argument is shape, and then you can have this match construct, which is kind of a branching based on the structure of this argument S. Okay, so what this means is, if S at its top level, and you can have patterns that drill into the structure, but here this is basic recursive functions on trees, and you might have written similar functions in your CS2 or 271 course, or 388.005. So what happens here is, if S matches this pattern, meaning it's a circle with a radius, then the actual radius gets bound to this variable radius. And then you can say, okay, here's the result that I'm returning. And here, just so this doesn't produce an exception, we have a default branch that comes at the end, which says if it hasn't matched anything so far, if it matches nothing so far, then this is the default or catch-all branch, and then we'll say, okay, it'll produce this result. Fair enough. So that's how you can do pattern matching on the case classes. And so now you've seen both parts. You've seen in fixtures how to build these object graphs. In this case, they're trees nested from case class instances. And you see here how to deconstruct them so that we can operate on them and basically process them properly. So this allows us to add behaviors to things that are, without the behaviors, just dead structures that don't have any specific behavior attached to them. So now the reason we need basically these companion objects for group and location that are not case classes, because we inherit from them. So point inherits from location and Polygon inherits from group. For this reason, to make them look like case classes, we have to have these companion objects, and the apply allows us to use the object itself as a function, and that makes it look just like we're constructing a case class instance. In fact, the way it happens is case classes automatically have a public instance variables. So these instance variables automatically become public, and for this to be the case with group or others, group or location, we have to say val. So if we don't say val in a non-case class, the instance variable will be private. Okay, that's the one thing. The other thing is case classes automatically have this way to construct instances without new, so the compiler automatically provides a companion object for them. And we're doing that explicitly for the non-case classes with the apply method. And then the third thing is, as we saw, case classes can automatically participate in a match, in a pattern that we use in a match expression. And for that to work with non-case classes, we have to provide the so-called extractor, which is called unapply. So if there's a companion object with an unapply, then the class can be part of a pattern, even though it's not a case class. So case classes are a very convenient way to achieve all of these capabilities without explicitly making the instance variables public, without explicitly having the companion object with the apply and unapply. But you can still achieve that effect by explicitly providing the companion object. So in Java terminology, the companion object is where basically the equivalent of static members would live. There is no such thing as static in Scala. The companion object gives you basically that single instance. It's a separate object that can have behaviors or members that are related to the corresponding class but are not instance-specific behaviors, but they're like static members. Okay, so that's that part. That should get us off the ground in terms of the Scala part. And the other part is really the conceptual part. So again, the midterm with its, the sample midterm with its solution should get you most of the way. I'll give you a brief overview. So if you look at the screenshot, what's being drawn here? Well, there's obviously a little circle here, then there's a rectangle, there are a few more rectangles. There's the purple circle, then there is the light blue polygon, which is composed of line segments. And then there is this shrink-wrapped rectangle all the way around. So it's the smallest rectangle that contains all of these shapes that are within it. And that's called the bounding box. Okay, conceptually, that's the bounding box. And what are we drawing here? Well, let's look at the main activity. Main activity doesn't say much. It's the situation we discussed in the other video. The main activity loads the main layout, and the main layout says that it has this draw widget, and that's where it's determined what gets drawn. and the complex group gets drawn here. Okay. So what you're seeing on the screenshot, minus the bounding box, now everything other than the bounding box is this complex group. So we have to look here. Well, this has a small circle of radius 20. Then there's a rectangle that happens to intersect with the circle in such a way. So circle has a radius, circle is centered at the origin, and rectangle has a width and a height, and you see how that matches up. And the rectangle starts at the origin toward the right and toward downward, okay? That's why the top left corner of the rectangle coincides with the center point of this circle, if you don't say anything else. Okay, now you might wonder, well, how do I get things that are kind of in another area of the canvas? And because the circle and the rectangle don't have ways to specify a location other than the radius or the size of the rectangle. Well, this is where location comes into the picture. So instead of building location information into each shape, which would be kind of a lot of code duplication, we say, whoa, let's do it cleverly. Let's say we can wrap a location object that provides this information around any shape, circle, rectangle, or a complex shape. Okay, doesn't matter. So this approach is the decorator design pattern, and decorator, there should be the equivalent here in the practice midterm also. Okay, let's see where that is. That is maybe a little further down here. Okay. Let's see, location. I know it's somewhere. Translate, it's called here, that's why. So what's called translate in the practice midterm is called location in our project. And the purpose of this is to say, well, the shape that I have is at some different place away from the origin. So x, it's x to the right and y downward away from the origin. And the child is, of course, the shape to which we're giving this location. And when you look at the fixture here, there is this group of rectangles here, okay? And it's 150 to the right and 50 down. Let's look at the screenshot again. See here, this rectangle, and then there's the little rectangle inside. But that's basically how you achieve this. So the location information applies to that entire child shape, whether that's a simple shape or a complex shape. So again, it's an example of the decorator pattern, and it allows you to dynamically apply certain behavioral or structural extensions to other variants, other implementations of a common abstraction in such a way that the common abstraction, the interface, is preserved. So that's why, again, in location, you have a child, so there is a has a shape relationship and an is a relationship, and you might say, oh, that sounds just like composite. But whereas composite has 0 or more children typically, this has exactly one child to which the decorator information applies. In this case, the location information. Okay? So that's how it works. The other, by the way, methods that you get automatically in a case class is equals. And if you need equality, you'd have to provide it explicitly in a non-case class. So that's the same as in Java. But for the case classes, you get it for free. Anyway, that's the idea. Okay, so that explains complex shape, which is the grouping construct. Then location, or translate in the sample midterm. And that's basically it. Then Polygon is based on group, and a polygon, the children of a polygon are points, and a point is represented as a circle with radius 0, so it's kind of a degenerate or extreme case of a point with radius 0 at a given location. That's how you can represent a polygon without introducing a lot more capabilities. Okay, so to draw, what you basically need to do is map your shape to these kinds of interactions with the canvas. So to draw a circle, you say, well, you just have to make that circle appear on the canvas. So we know that this circle has center point 0, 0, and it has a radius. And then Paint remembers the current style in terms of color, or whether it's stroke or outline, that sort of stuff. And the stroke versus outline, you see here, there's a red rectangle that's filled. Sorry, outline versus filled. That's the mode part here, the drawing mode. And the outer rectangle is in outline mode, and that corresponds to what you see here in the fixture. See here, so there is a fill, meaning that the child of this fill node should be solid, not outlined. And this, see how this fill propagates down to this rectangle. That's the small solid rectangle. But then the large rectangle is specified to be in outline mode. Okay. And then the circle here, the purple or magenta circle that we see here, is also in outline mode. And oddly, the polygon should have been in fill mode, but that's simply a bug here. And we just say, well, Polygon doesn't support outline. Because Polygon is implemented as drawing lines. So that's something you don't have to worry about. That would be a little more complicated. So polygons are always drawn in outline mode. Okay, I'm just noticing this now. It's been in this example for a while, and I'm just noticing it now. But that's okay. So don't worry about it. So Polygon will not pay attention to fill or outline. Anyway, so this fill applies to the child. But if there's something more specific around a descendant, the more specific thing will apply. So as the draw visitor looks at these different cases, so as it sees a fill, it says, okay, let's switch the style to fill. So you need to look at the available styles for Paint, and so on. That's how that works. So now the question is, what about this bounding box? And let's see what the draw widget does. Well, so the draw widget, the first thing it does actually is compute the bounding box for this overall shape that it draws, and that's the surrounding rectangle on this screenshot, that shrink-wrapped rectangle around the whole thing. And it does that so that it actually finds the shape, and it can kind of center the canvas around the shape. because this shape might not start at the origin. So we want to kind of center, focus, zero in onto that shape. And to do that, it says, okay, let's move to the top left corner. Let's kind of do this so-called affine transform of the canvas to the top left corner of the bounding box. That way we will zero in our view. It's like scrolling to the actual shape. Then we'll draw the shape. Then we'll draw we'll create the draw behavior, which is the Scala equivalent of a visitor. Then we'll draw the bounding box, then we'll draw the shape, and then we'll kind of transform back to the original coordinates. And this transforming back and forth, this is something that you will need to use in your draw visitor as well. And a similar idea you will probably need to use in the bounding box visitor. It has to do with one particular kind of decorator. Anyway, that's that. And let's see what else. Yeah, the bounding box is easy for most cases, really, especially for circle, and that's why that one's given. For rectangle, it's even easier. Every bounding box is described as a rectangle at a particular location. So all the results that you return for any kind of shape, it must always be a rectangle at a specific location. Okay. Now the algorithms are given in the practice midterm solution. So for bounding box, it is here, right? Problem 6. And here is the algorithm for visiting a complex shape. So you can see how this kind of shrink wraps, it looks at each child of the complex shape. And so it starts with an infinitely small rectangle, as you can see here, right? So the left x is the max integer value, and the right x is the mean integer value. So it's infinitely small, right? Going the other way infinitely. So then every time it looks at a child, it kind of expands the rectangle. So it's the opposite approach of shrink wrapping. Every time it sees a shape, it makes sure that it expands the rectangle just enough for that shape to fit within. And that's what we're seeing here. All right. So you can essentially use the same conceptual approach and just translate it properly to Scala. And there should also be a, let's see. The printing is not so interesting, but there is the drawing for the translate, for example. Remember, the draw in the sample midterm is not in the visitor, but it's included behavior in the actual shape classes. So which is again only to show that it can be done, but it's usually best to have a separation of concerns between structure and behavior. That's one of the nice things of the visitor pattern. Okay, let's see if there are any other points we need to cover. Well, the process here is the usual. Make sure you keep things simple. So, for example, the difference between in size between the code skeleton that I'm sharing with you and my solution is only about 70 lines. So you should definitely not need more than 100, 120 lines or so. Around there. It doesn't have to be very exact. And then the question is, when are you done? Well, let's go here. when you're done, all the tests pass. Yes, there's another little thing we need to cover. So you should see this, okay? Now, you might wonder, well, how in the world can we test what's drawn? Are we comparing images? I mean, that would be one way to do it. And we'll get there shortly. The S coverage, by the way, just so you can see this, I can say run the tests with the coverage data being collected in the process. So this ties to the discussion on the Facebook group, but the testing happens, but in addition, it produces this coverage report at this location. Okay, and we can open this in the browser. And how cool is this? So here we can see this coverage report, and we actually see these two criteria, the main ones really: statement coverage, meaning how many or what percentage of statements in the source code is covered, and then branch coverage. For example, if there's a loop or a conditional, it makes sure that every branch in the code gets exercised, but not necessarily every combination. So I think I mentioned this in class. So if you have two consecutive if-else statements, branch coverage means each branch in each of these statements is exercised at least once, but not necessarily all possible combinations, like the then branch in the first one with the then branch of the second one, the then branch in the first one with the else branch of the second one, and so on. Not necessarily all these combinations. Could be then, and else. So just 2 test runs. Instead of combinatorially, you would need at least four to cover all combinations, which is path coverage. So path coverage is usually considered a much higher standard. So here, by S coverage, it's not included as one of the statistics. Okay, so if you can achieve a high coverage, that would be good. And let's see, even if you have some red pieces in there, not 100% coverage, it's still okay. But so let's look at the actual test for some of these things. So bounding box, it simply says, well, what's expected? That's very simple. Okay, so that's a simple flat spec, behavior driven spec. So it says, well, the bounding box for, let's say, the simple circle should be a square with a circle in the center, just like you would expect, where 50 is the radius of the circle. For size, you have to keep in mind it counts only actual shapes, so location and group and fill and those things don't get counted. Okay, just guide yourself. When you implement the size behavior, let this be your guide. Now draw is interesting because this uses what's called mocking, where we're expressing the dependency as a fake object. So in other words, we're testing our draw behavior, but normally the Android environment, the runtime environment provides the canvas and the paint. But we want to do a unit test outside of the Android runtime environment. So that's explained in this comment here. And what we can do by using something called mocking, and there are different implementations of mock-based testing, or you can even roll out your own, but it's convenient to use a framework for that. We can create fake objects that have the same interface, and then we can create this object that keeps track of the order in which other objects interacted with these mocks, with these fake objects. And then we can say, well, if we draw a simple location, which is a circle at some location, and you can look at the fixture, Then through the order object, we verify what interactions there were with one of the mocks. So we can say, well, there should have been, the first thing that should have been done to the canvas is a translate with these arguments. Then the draw rect should have been invoked on the canvas with those arguments. And finally, the translate method back to the original place should have been invoked on the canvas. See, so this is actually pretty cool. And then for the complex group, even though this draw is a fairly complicated recursive method, ultimately what gets done to the canvas is some linear sequence of drawing steps. And these are the steps. And the tricky piece is, and you should really keep things simple, avoid confusion. When you get to the draw polygon, just draw the lines in between every two consecutive points in the polygon. Then it'll match this. If you draw the polygon differently, it probably won't match this. So this test will not pass, although you might still see the polygon in the same way. That's why I would recommend just go down this path and try to use draw lines. Okay, so this is it. I hope this is effective in getting you started. And we'll take everything else over to the Facebook group. So see everybody soon.